Hello everyone. Today I'm going to present an algorithm about solving linear programs. This is a joint work with Shenhua, Armory, and Hengjie from Columbia University. Let me start. This talk is mainly consisting of three parts. The first part is the introduction, and the second part I'm going to focus on our LP result, and the last part is basically a summary. So let me remind all of you what is optimization. So usually optimization has two cases. The first case is called a convex case, and the second case is called non-convex case. And mathematically, you can think of you have a function f, and you're going to find some like a parameter w, such that f of w is minimized. So usually, no matter in which case, you run the same algorithm. At the beginning, you choose some random base to be initialization point, and then at each iteration, you are going to update your WT plus 1 based on WT and also grading information. So therefore, the running time of optimization algorithm usually has two parts. The first part is called like number of iterations, and the second part is called cost per iteration. So usually, the cost per iteration can be as big as the input size of the original problem. So naively, this algorithm will take like a capital T times capital N time, where T is the number of iterations and N is the input size, because every iteration you need to read all the problem. And the question is, can we do better? So the hope is there some way to read the input only once, and then usually in the future, and in every iteration, you only spend sublinear in input size. So therefore, like ideally, if capital T times small of n less than capital N, then you actually can get the input size time algorithm. And this algorithm is essentially optimal because you have to read the input once to solve this question. And now the question is, how do we speed up like such greedy algorithm in general? So over the last many decades, there are a lot of effort have been made to trying to like improve the cost, improve the number of iterations for such algorithm. And in this talk, we will focus on a very different angle, which is trying to improve the cost per iteration of the algorithm. So linear programming is one of the very definitive examples in convex relation. And usually you are giving a matrix A and a vector B and a vector C, and you want to solve this minimization question under linear constraints. And on the current Earth, there are several problems can be written as linear program. So for example, energy industry and transportation system, food and agriculture, manufacturing. LP is also known to be like one of the top 10 algorithms in the 20th century. So in the second part of our talk, I will focus on applying our linear program results. I will start with definition LP and also like give you a history of the LP, and then I will print our results, and finally I will give you some high-level idea of our techniques. Let's go to the second part now. What is a linear program? So usually, linear program can be defined as follows. You are giving two vectors and one matrix, and say like your matrix and the vector, they are like this. And you can turn your orange, you can actually turn your green matrix into this linear constraints, and this green linear constraint, they are going to corresponding to a convex region in 2 dimensions. Now, if you look at your orange numbers, and they are going to decide an angle in 2 dimensions, like this. And now your task is trying to push this line while keeping the angle of this line until it touch the boundary of your green convex region. And once this orange line touch the boundary of this green region, we say we solve LP. So solving linear program has a very, very long history. Almost 200 years ago, people already studied solving some linear inequalities. And the very first algorithm for solving linear program is called the simplest algorithm. This algorithm is developed by Dantzig in 1947 during the Second World War. This algorithm is doing a very good job in practice, but in theory, it has an impending time, requires impending time in the worst case due to the Klein-Mitten counterexample in 1973. Therefore, like whether LP can be solved in polynomial time is a long-standing open question. So in 1979, ellipse algorithm developed by Kitchen is the first time we know how to solve LP in polynomial time. However, this algorithm has some weakness. For example, this algorithm runs very slow in practice. Almost no one can actually use it. So therefore, another very exciting question is, can we actually develop some LP algorithm which can be analyzed in theory in polynomial time and also can be used in practice? So in 1984, Kamarka proposed such an algorithm called interpoint method. This algorithm has a good performance in both theory and practice. Another advantage compared to for this algorithm compared to ellipse method is this algorithm only takes root n iterations. However, ellipse method takes n iterations. Almost all the later works, if they want to improve the running time of linear program, they are basically focused on this interpoint method because the number of iterations is quite small. Since Vaidya 1989 algorithm, the fastest algorithm for solving dense full-rank matrix LP remains n to the 0.5. This n to the 0.5 barrier is remained for 30 years. Two years ago, in a joint work with Cohen and Lee, we actually show how to solve linear program in n to omega plus n to the 2 plus 106. And however, it's unclear whether it's 106 is necessary. And in today's talk, I will present a result which improves this 106. Let's go to our main result here. And in today's talk, we present a result which is a joint work with Shunhua, Armory, and Hengjie. And this algorithm takes only n to omega plus n to the 2 plus 118 time to solve LP. So here, omega is the equivalent of matrix multiplication. N to omega is the time for multiplying an n-band matrix with another n-band matrix. Currently, omega is roughly equal to 2.37. And in the community, some people believe that omega could be 2 eventually. I would like to also justify why our algorithm is optimal in some sense, because even you want to solve a linear system in the worst case, it already takes omega time. So some linear system means you just want to solve AX equal to B without this C transpose X in LP. So if omega equal 2, linear system takes like n squared time. However, LP will stop at n to the 2 plus 118. Another very remarkable result I want to mention is, since our paper is online for 6 months, and by Brandon, he simplified part of our algorithm, however, the running time remains the same. So therefore, a very interesting question is whether we can actually solve LP as fast as linear system. Mathematically, can we actually completely remove this additive term 1/18? So this question remains open. We don't know how to do it yet. Now let me give you a brief history of the solving linear system and solve linear programs. So here is a picture. The x-axis is the years, and the y-axis is the running time of the exponent. So solving linear system boils down to solving matrix multiplication. So the naive time of solving matrix multiplication takes n cubed time. The first truly subcubic time of solving matrix multiplication is due to Strawson in 1969. This algorithm runs in N2 2.81. After that algorithm, there are a lot of people trying to improve the exponent. For a while, people stuck at 2.5 until the Cooper-Smith and Wiegand tensor, it can break the barrier of 2.5. So over the last 30 years, the running time of solving mesh marcation improved very slowly, as you can see from this picture. Now let me briefly remind you the running time and the history of solving linear program. At the beginning, solve linear program takes exponential time due to density algorithm. Kitchen gave the first algorithm that can solve LP in polynomial time. Then Kamarka improved it to N2 3.5, and Renigan and Vaidya improved to N2 3. And Vaidya then, like in 1989, improved it to N2 2.5. As you can see from this picture, over the last 30 years, the running time of solving LP in the worst case for the full rank dense matrix remains N2 2.5. However, in the result by the and Cipher, they do improve the LP running time for some cases when matrix is low rank or sparse. 2 years ago, in my joint work with Cohen and Lee, we actually show like solving LP can be done in N2 omega time, which is the first time solving linear program time matches the linear system time. However, if omega equal to 1 day, our algorithm will stop at 2.16. So in this talk, we show how to shift the 2.16 to 2.05. As you can see from this picture, the 0.5 is already very close to 2. Another very remarkable result about mesh marcation in this year is by Elman and Williams. They improved the exponent of mesh marcation. So in the rest of talk, I will focus on the present high-level idea and techniques of our algorithm. So basically, LP boils down to an iterating algorithm, and it has routine iterations. Each iteration it involves several very basic numerical linear calculations. For example, matrix vacuum marcations, matrix mesh marcation, or even you need to compute a matrix inversion. So I will not explain why that algorithm suffices solve LP. Instead, I will only present the computation bottleneck. Let me give you an overview of a very oversimplified algorithm of Vaidya's algorithm in 30 years ago. Let I denote the counter and W is the weight we are trying to do the gradient descent on it. So at the beginning, we need a while loop to check if we already reached the routine iterations. And let's think of, we have some very cheap oracle where you take the W as input and you will output of H. So in line 4, the major task we need to compute an inversion of the constraint matrix times the diagonal matrix times the transpose of the constraint matrix. In line 5, we need to update the weight vector W based on W plus P times H. And then we increase the counter I, and we finish the while loop. So the naive implementation of this algorithm will take N2 omega plus 1/2. However, Vaidya can show you can actually do better. By doing some trick, you can get N2 2.5. This algorithm has routine iterations. And as you can see, the bottleneck is from line 4 and line 5. It takes N2 omega time per iteration. The cost per iteration is the following. In line 4, it computes matrix P. This takes N2 omega time. And Vaidya showed you only need to take like N squared time over routine iterations. And in line 5, you need to compute P times H. This takes N squared time. As you can see, if you want to improve this N2 2.5 to something else, you need to resolve like the bottlenecks in both line 4 and line 5. The major technique we are using is something called like compression. Here, one compression technique is called sketching. I will give you an example here. So if you Google sketching, and usually the word is saying the following: you have someone's picture, and now like you want to draw a sketch of this picture. Basically, what you do is you can just keep a boundary of this picture, and you can not many details like color and background. However, if you look at right hand side picture, you can still tell who is this person. So here, let me give you an overview like of our compression techniques. So there are two kind of techniques. One is like a randomized compression technique. The other is like a deterministic compression technique. So in randomized compression technique, the first technique called sketching, where like you can think how matrix R is a very fat matrix, every entry is a random Gaussian. And another different compression matrix is called like a sampling matrix, where D is a diagonal matrix, like B non-zero entries on diagonal, B is roughly root 10 here. And in order to make the algorithm work, you need in every iteration, you need to control the error generated by sketching or sampling. Another technique is called the compression technique, where like they are trying to maintain a vector, which is approximation of the H. And here is a summary of four like work before us. And all the four works they can achieve like n to the omega plus n to the 2 plus 1 over 6 time. And the first algorithm, there is the first work, they can get n to omega time for solving LP and using randomized sampling. And it basically sample on the right-hand side of the matrix P. And the second algorithm and third algorithm, they are both using sketching. And one is sketching on the left, the other is sketching on the right. And the last one is a compression technique used via like a vector maintenance, trying to maintain a vector H. And it's unclear for all of this algorithm how to go beyond the 1 over 6. And in today's talk, we actually improve this 1 over 6 to 1 over 80. So here is some high-level idea of our algorithm. Our algorithm is basically a lazy algorithm. Let me define a P matrix which takes the W as input and basically compute an inversion of the constraint matrix times the diagonal W times the constraint matrix transpose. So think of you have some online sequence W1 to WT and also H1 to HT. Suppose someone give you this sequence. You don't need to worry about how do you get this sequence for now. And suppose like WT minus WT plus 1 is nearly sparse. And your job is going to like output another sequence V1 to VT such that the difference between VT, they are exact sparse because this is easier for you doing math. The guarantee we hope is f of VT is roughly f of WT. The function f can be many things. For example, identity function, P function, also P times H. Here is a concrete example. Think of you have a dog, say like W your dog location, and V is your human location. And usually when human walking your dog, you need to use leash. And the leash has some limitation of length. You cannot hope every dog is like this dog, it can leash themselves. So therefore, like in the practice, in order to make sure dog and our kid, they are not hurting themselves or lost, human need to take the other side of leash. You cannot like the kid or dog keep both sides of leash. However, in the meanwhile, you still want to do something easy, like making a phone call or writing some papers. So here is a concrete example. Say like this is dog location, and this blue ball is a human location. At the beginning, they are in the same location. Now the game is that when dog is moving, human is trying to chase the dog. If the leash is going to broken, human need to move their location. If the leash is not going to broken, human need to move. Let's say when dog move this way, and in this case, leash is going to broken. And therefore, like a human need to move. And in next move, if dog moved here, if dog moved here, in this case, human doesn't need to move. The right choice of human should just stand at original location. So when dog move again, and in this time leash is going to broken again, and then human need to move. And therefore we just repeat this whole procedure. And every time when dog is move, human need to decide move or not move. And after many moves, and you can look at total length of the trails for the dog moves, which is orange lines. And you can also look at the total length of trails of human moves, which is this blue lines. You will see the total length of blue lines is going to be much smaller than the total length of orange lines. That's basically how we improve our algorithm. Here is a comparison between two algorithms. In my work with Cohen and Lee, we get n to omega plus n to the 2 plus 1 over 6. And the major idea we explore the changes are changed slowly in this algorithm. And therefore, like when dog is move, Superman need to chase, because Superman need to move very fast. And eventually, if you look at the total length of Superman moves, it's much more than the total length of dog moves. And in this new work with Shunhua, Valmy, and Hengjie, we can improve this 1 over 6 to 1 over 18. And we basically pull the changes, all the changes are changing very slowly. So in the game, you are not only have dog and human, you also have a kid. And so the task is kid need to chase the dog, and human need to take care of both kid and dog. And like this. And again, eventually you just check the total length of trails, you will see they are much smaller. That's how we improve the 1 over 6 to 1 over 18. Now let me give you some summary. In today's talk, we plan an algorithm that solve LP n to omega time plus n to 2 plus 1 over 18. So there are many interesting future directions. So for example, can we apply our ideas to practice to get some practical algorithm for LP? Second, is it possible to generalize such ideas to some graph type LP, for example, matching or flow? Third, can we generalize ideas to some other convex setting, for example, semi-definite programming? Fourth, can we generalize ideas to non-convex formation, for example, deep learning? Last, can we actually generalize ideas to quantum algorithm? So thanks for watching this talk. This is our archive link, and the archive title is slightly different from today's talk. And if you have any questions about the talk or this paper, feel free to write an email. And thank you again, and enjoy the rest of the talk.